The next very important topic in studying acids and bases is to understand the difference between a strong acid or strong base and a weak acid or weak base. And this understanding is really going to control how we approach many of our calculations. I've already asked you to memorize these strong acids and bases. This is key to being able to do many of the calculations that are coming up, is to know and be confident in your knowledge of the strong acids and bases. By definition, a strong acid is something that dissociates completely. So when we're dealing with strong acids and bases, we're dealing with complete arrows. And these really fit the Arrhenius definition of acids and bases. So these are the strong acids, and anytime you're dealing with one of these acids, this is how they will behave when they are in water. They simply dissociate completely to produce H+ and the counter ion. The strong bases also dissociate completely. They are salts formed with the metals from what I refer to as the big little b on the periodic table, and hydroxide ions, and those dissociate completely. So this is a visual here. Okay, if we start with this amount of hydrochloric acid molecules at equilibrium, or once we've allowed it to complete its reaction, we will have the exact same amount of H+ and Cl-. So the molecules will be fully dissociated in the solution. When we're dealing with a weak acid or base, we're going to need to use the Bronsted-Lowry definition because we're going to be looking at equilibrium. A weak acid or a weak base is something that only partially dissociates in water. And you're going to see that a lot of these will dissociate less than 5%. So the way that you can recognize them is that they've got the Cu group, so organic acids tend to be weak acids. Okay? And hydrogen fluoride is another weak acid. It's not on the list. Okay? We'll discuss structurally why some acids are stronger than others. These are going to have equilibrium constants associated with them, and they'll have a small Ka value because the equilibrium does not go very far to the right. Weak bases are those organic bases that I discussed earlier. So you'll see they've got some carbon and hydrogen, okay, and then they've got the nitrogen in them, and the nitrogen is where there's a lone pair that accepts the proton. Now the key here is to understand that when you've got a weak acid or base, it doesn't dissociate completely. So when you look at the before and after, say I had 100 molecules of hydrogen fluoride to begin with, I might only dissociate 5 of those. So if it was a 5% dissociation, I would only dissociate 5 of them. The other 95 molecules would stay intact. So when you look in the solution, there's fewer H3O+ ions in the solution, okay, which is going to affect things like the pH. This table here shows you the relative strength of the acids and bases. So our strong acids are up here, okay, and as we move away, something like ammonia is a very weak acid. So it's very unlikely to donate a proton. What we've got on the opposite side are the conjugate bases. So this is the perchloric acid, and this is the perchlorate ion, and these are related, connected by one proton. So this is the acid and this is the conjugate base. Now when you're looking at a conjugate acid-base pair, the stronger an acid is, the weaker its conjugate will be as a base. So the more likely this is to donate a proton, the less likely this is going to accept a proton. And that makes sense because the farther the reaction goes towards the products, the less likely the reverse process is going to be able to happen. We'll study that concept quantitatively a little bit later on. What we will do now, though, is talk about the structure structural implications of a substance and how you can look at the structure of a substance and decide the relative strength. So when you want to compare two molecules to one another and decide which one is a stronger acid, you've got two things that you need to look at. You need to look at the strength of the bond that needs to be broken. The stronger the bond, the weaker the acid will be because the bond needs to break in order for the proton to be donated. The other thing to consider is to consider the polarity of the bond that needs to be broken. So the more polar a bond is, the stronger the acid. The reason for that is, as you'll see in the case of having oxygen present, okay, the oxygen is drawing the electron density away, okay, and allowing for the hydrogen to be donated more easily. So we've got a few different kinds of acids. We've got hydrophilic acids, which are ones that don't contain oxygen. So we call them like HX acids. They've got H, the hydrogen ion, and then they've got X, which is a halogen. When we're comparing these, we want to look at the comparative bond energy. The HF molecule holds the strongest bond because the fluorine is the smallest of the atoms in this group. The closer the hydrogen and the fluorine can get to one another, the stronger the bond is going to be between the two. So as we go down this group, the bond to hydrogen gets weaker and weaker, and therefore the acid gets stronger and stronger. Okay, so HI is the strongest of those acids. And the HF bond is significantly strong. Okay, so it's a significantly weak acid, hence the double less than symbols here. Oxoacids are acids that contain hydrogen. And we've got a couple ways that we can compare them. So we can compare oxoacids that have different central atoms but have the same number of oxygens. So HClO3, HBrO3, and HiO3. And in this case, what's going to happen is that the strength is going to increase with the electronegativity. So as we go up this group, the atom becomes more and more electronegative. And what that is going to do is draw the electron density away from the bond holding onto the hydrogen. Okay, so if we look at this molecule here, okay, we can see that this is what the structure is. So the chlorine is in the middle, there's the 3 oxygens, and then the hydrogen is attached to the oxygen. The more electronegative this chlorine atom is, the more it's drawing electron density away, and what the impact is a weakening of this bond, which makes it stronger. Now, if you've got the same central atom and a different number of oxygens, so we've got this list here of HClO4, HClO3, ClO2, and ClO, the rule is that the more oxygen there is, the stronger the acid. And this, again, is related to drawing electron density away from this OH bond that needs to be broken for the substance to act as an acid. The more oxygens, the more electron density is being pulled away, and the weaker this bond becomes, and it's more acidic. If you look back at the list of strong acids, HNO3, H2SO4, HClO4, those are all the molecules that are holding the maximum number of oxygens with those central atoms.